Hello everyone and welcome to another video. So today I'd like to continue our discussion on artificial intelligence, machine learning, and data science by taking a look at one of the foundational concepts that we're going to continually come back and revisit as we explore topics in the future. And that topic for today is regression using numerical optimization. So if you spend any amount of time researching this field, you've undoubtedly come across a lot of different textbooks, a lot of different prominent data scientists that talk about how a lot of these concepts like artificial intelligence and machine learning really, they boil down to regression, and if you take actually one more step of a generalization, that really is talking about optimization. So today what I'd like to talk about is look exactly at how those relationships between regression, optimization, AI, and ML, how do those all come together in several very simple kind of academic cases, which later on down the road will expand upon to more practical examples and implementations. So the game plan for today, I want to spend a little bit of time talking about the roadmap, because the roadmap for the discussion today actually is going to turn into a roadmap for probably the next 3 or 4 lectures where we're going to expand on some of these subtopics in greater detail. So today, let's start off by talking about just, what is an introduction to regression? It may have been a little while since you took your last statistics course and talked about how to build models using data. So let's talk about this at a very high level. And then let's jump into a very specific case of regression. Let's look at the case of what's sometimes known as ordinary linear regression, or just plain old linear regression. We're going to see that if we're able to set up a problem like this, it's actually quite handy, because then we're able to obtain a solution via what's known as sort of an analytical least squares approach. Okay? This is great because it gives you sort of this closed form analytical way to do this, but what if you didn't have that approach? Could we instead use a numerical optimization routine or scheme to get basically an equivalent answer? And we're going to see that to do this, you kind of need 2 major components. You need to be able to calculate the gradient of a error or loss or cost function, and then you also need to be able to implement some type of numerical optimization routine to use that information, okay? So that's the game plan for linear regression, and this is all fine and dandy, but what we would also like to do is see, can I apply some of these ideas to a more generalized regression case where we might have a model that is nonlinear or more complicated, okay? And we're going to see that this is basically the situation where, okay, you might not have analytical tools available to you, but I can basically copy and paste this idea of using a numerical optimization routine to this problem here as well. So the numerical scheme is not going to really care if you have a linear or a generalized regression case. The same ideas are going to be able to be applied and used, and I want to explore that in these 2 concrete cases. So that's the plan for today. So if that sounds like fun, why don't we go ahead and jump into this first topic and just talk about an introduction to regression. All right, so let's talk about basic regression. So modern data science, as the name implies, focuses around data sets. So one way to think about a data set is a collection of samples or data points. So one data point or one sample might be something like an input, let's call it U1, which somehow results or is correlated to some output D1, okay? So this is your first data point, and this is a real simple case, right? And you could have another data point, let's call it U2, which produces a completely separate set of outputs, D2. And again, you can just repeat this all the way for UNS producing DNS. So in this case, we have NS number of samples or examples in our data set, right? So the idea here is, again, we're going to use U to denote the inputs, or maybe you can think about them as independent variables. And I'm going to say independent variables, right, plural, and denote this with a vector bar, right, to help us illustrate the fact that there could be more than a single input to this system, right? There could be things like the time of day matters, so does the ambient temperature and the ambient pressure, and maybe even what you ate for dinner last night, right? You can collect all of these inputs which might have some bearing on the process, which will then produce some output or some desired result D, which again will also denote with a vector to just show that this system could have a vector output. It doesn't have to output just a single scalar, right? So this is the idea with the data set, and it's really simple. As you can see, it's just basically these pairs of inputs to outputs, okay? Now, the idea with regression is really just talking about the process of trying to find the relationships between those independent variables and the dependent variables, right? What is the process that takes an input and generates an output, okay? So what we would like to do, though, in this case is that process could be very complicated, right? Going from U to D is some real process like the weather or something like that, and it's incredibly complicated. So instead of trying to do that and trying to understand that exactly, we want to generate some kind of model that is going to predict or estimate those outputs if we give it the same inputs. Okay, so this is what we're talking about in a very general sense, right? Our model is, this is a very generic form. It's basically saying this is some function. It can be as complicated or as simple as you want, but it has an input as U, right? It's the same U's that we saw over there in the real system. This model also has tunable parameters. There might be all these different knobs or all these different parts of the model that you can change, and then you're free to move around and mess with. And therefore, you're going to make this model be able to spit out some output. Let's call it Y. So this is what I wanted to distinguish between Y and D here. So Y is the model's output or the model's estimate of what this dependent parameter is going to look like if you give it the same input U, right, that both the real system and our model consume. Okay? So the idea here is that we would like this model to be really good so that Y is very close to D for all of these different cases, right? So if I give U1 to the model, hopefully my model produces a Y1 which is really close to D1, right? And if it does, that's great, but in all likelihood, it's probably not going to, right? There's going to be some difference, okay? So one way that's very convenient that people use to measure this difference is, it's pretty simple, right? Just take the difference between what the model produced minus what the actual answer should have been, all right? So this is sometimes referred to as the residual, okay? And as you can see, it's really simple. It's just the difference between the model and the actual label or the actual result that we're looking for. Okay? So graphically, I like to think about it like this, right? The idea is, okay, we have some input U which is known, right? Now, the idea is usually what happens is that in the real system will take these inputs and somehow do something. I don't know. I've denoted it here with a bunch of question marks because this could be, yeah, a real process like weather or, a car moving down the road. It could be anything. But the fact is, it's super complicated and maybe we don't understand it completely. This output is going to produce, that input is going to produce some output here. This output we are calling as D. You can think about this again as the desired output or the real output. Sometimes in the context of AI and machine learning, this is sometimes referred to as the label of the data because it is what the output should be if you feed it some kind of input, right? This is the label or the desired output, right? Now, that is great, but what we are interested in is instead this model that we're making, this simplified system or an approximation of this real system looks like this. And you give it this same U, and what it does is it produces what we're calling Y. Okay? So Y is our model's estimate or our model's prediction of what the system is going to do if given the same input, right? And if the two are not the same, we just take their difference and we generate what's called the residual, right? So again, maybe to help us set the stage for this, I like to think about these in concrete terms. Again, think about this as, let's call this weather prediction, right? Which is very, very complicated, right? There's tons of information that goes into predicting the weather, right? So this U, let's say we boil it down to only a couple of parameters that we think are important. Like, let's call it time of day and ambient temperature and ambient pressure. And the real system is going to be able to predict, or it will produce. We know that if you know all this information, the real system will have some output, like what the weather is going to be. Is it going to be rainy, cloudy, what's the temperature, all that kind of stuff, right? But we're trying to generate this model or this estimator, which is going to take those inputs and now try to generate a prediction of what the system's going to, or what the weather is actually going to be like, right? The idea here is what we're able to play around with this model. The beauty about having the model is that we can vary these model parameters. I'm going to call them X bar, right? So X here is the tunable parameters of the model. So we can change this entire vector X. This vector X, it might be 1 item, 2 items, 1,000,000 items. Depending on how complicated this model is, this vector could be large or small. And the idea, though, is we have absolutely free reign of being able to change this vector x. Therefore, we change this model, and the goal is we want to be able to change this model so that the outputs match the real system's outputs in as many cases as possible, right? Because you got to remember, what we're talking about here is you're feeding in a given input, which will produce a given output in both of these cases, right? And now what we have to do is we would like to go and see, can my model match data point 1? Can it match data point 2? Can it match data point 3? Can it match? And you may have thousands or millions of examples. And now the game plan is, how do I pick one vector x for this model so that it matches as closely as possible to as many data points as possible, right? So that's the idea with regression, right? That's what we're gunning for. So now let's look at a concrete example of how can we work up a really simple problem to illustrate this idea. All right, so let's just make a few changes to this. So instead of introduction to regression, let's talk now about one of the most common forms of this is linear regression. And for this case, let's make another small change just to make it easy to deal with. Let's not consider vector inputs and outputs. Let's just consider scalars. So I'm just going to delete these vector notations on all of these data sets. Otherwise, it's still the exact same thing, right? So now we've just got one input producing one output, right? So again, just delete all those, blah, blah, blah. Okay, great. All right, so in the case of linear regression, what we'd like to do is, there's actually a lot of different ways we can choose this function, but probably the easiest way that we can choose the function for our model is, since we want to do linear regression, let's just choose a linear, or more appropriately, maybe an affine function here, which looks like slope times independent variable plus an offset here, right? So this is an affine function. And again, I just want to point out right here that you don't have to choose a linear function in order to form this into what's known as a linear regression. There's plenty of other examples of how you can do this for things like polynomials or other types of function fits here, which still fit into this linear regression framework. But to keep things simple, let's just look at pretty much the simplest case. And I think when we're done with this, you'll be able to see how this can extend to other cases and other types of functions, okay? So the idea here is, again, here's our model of f, right? So again, the way I like to think about this, since I'm a kind of a controls and systems engineer, is I like to think about this as block diagrams where you got an input coming in, and again, this thing spits out an output y, okay? Now again, we said that there's this tunable parameter x, right? This model has tunable parameters, right? There's two of them right here, you can clearly see. So let's again stack these two tunable parameters up into a vector x, where we got an x1 and an x2, and x1 is just the slope of the line, and x2 is just the offset. So really, all we're talking about here is fitting, well, we're doing line fitting, right? If we have some data here, I want to fit this with the line. And in fact, let's make up some data. So I'll show you a screenshot over here. We'll take a look at this closer when we jump over to MATLAB, but here's some data, right? It's some matched points of U and D's, right? So this is what the actual system does, right? And you can see it looks a little bit linear. I mean, it's definitely, I mean, there's for sure not going to be one line that goes through all of this data, right? But you can see it's got a roughly linear trend. So I think this is reasonable that we would maybe try to fit it with this function or this model, okay? So that's what the data set looks like. So now what we want to do is look at a couple of different things. So maybe one thing we should chat about quickly is, I do want to draw your attention to this, is let's define another variable. Let's call it NP. So this is the number of tunable parameters in your model. So in this case, you can clearly see there are two. So again, the number of parameters, or the tunable parameters, are going to come into play in some future lectures, as is NS, right? This was the number of data points, or the number of samples, or back in that picture we showed earlier, it's basically the number of X's that were on the plot, right? So both of those two things are going to come into play a little bit later, but I just want to draw your attention to that now, okay? So we've got our whole setup, and now what we would like to do is, we would like to fit the model to the data set. In other words, what we really would like is, it would be awesome if we could get this model's output, right? This whole output, this left-hand side is y of c, right? It's basically the output for a given input uc, right? And it would be awesome if this equaled the actual data, right? The actual result, or the actual dependent variable of the system, or the label of the system, if you want to think about it that way, right? If these two equal themselves, that would be excellent, right? But as you can probably imagine, this probably isn't going to happen. In fact, we can see that more clearly if I go ahead and, let's go ahead and write out a few of these terms actually. So let's do this for c equals 1, right? So that's really easy. So this is basically just going to say that we would like the function for u1, right? So that's this guy up here. So it's x1 times u1 plus x2, right, is equal to d1, right? That's this whole expression for c equals 1. Let's look at the c equals 2 case. So again, that's the slope, x1, times now the second input plus the offset is equal to the second actual output, right? And again, let's do just a few more so we can get the pattern here, right? So this is x1 times u3 plus x2 equals d3, all the way down to c is equal to the number of samples or the number of data points you have in your set or that you are considering. This comes down to x1 times u(ns) plus x2 is equal to dns, right? Does everyone see where we're going with this? Let's go ahead and write this in a matrix format, right? So I could write this whole thing as basically, let's pull out x1 and x2 here, right? And what this does is, again, that first row here just becomes, what is this? This becomes u1, right? u1 and then a 1. Right? And then we get a u2 and a 1, and a u3 and a 1, and all the way down to a u(ns), right, and a 1. And that has got to equal, what is this, d1, d2, d3, blah, 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 dns. Does everyone see what this looks like? This looks like a big old A times x is equal to b, right? Okay? And now what's interesting about this is, again, think about the shape of this A matrix, right? This A matrix is probably, if you have a significant number of data points, right? If this is like 10 or something like that, or 100 or 1,000,000, right? This A matrix is going to be incredibly tall and narrow, right? And then again, if you have that case, we basically have it's an over-constrained system, if you want to think about that from an over-constrained versus under-constrained system, right? This A matrix, it's only got 2 columns, and it's very unlikely that this B vector is going to be in the column space of this A matrix, right? So in all likelihood, you are not going to be able to solve this AX equal to B exactly, right? So if that's the case, we're going to have to go to a couple of other techniques. So let's go ahead and take a look at solving this via what's known as kind of an analytical least squares approach. Oh, and actually, sorry, before I erase the board, I do want to maybe just circle back to what I mentioned earlier, right? We talked about how this linear regression had a linear function, but it didn't have to be linear, right? So maybe this is a good point to just show, you know, what if you wanted this to not be just a pure linear function? What if you wanted this to be like a quadratic, like something like a, you know, I'll just add plus x3u squared. Right, again, that's probably not the best nomenclature because I've got the x1, x2, and x3 kind of in weird orders of coefficients, but you can see how this would work, right? So now you just now have a third element, and this is like the quadratic term, right? So all we're doing is you would just introduce one more variable into your tunable parameters, right? And then all that ends up happening is you just got to modify this a little bit, right? So I guess this becomes plus x3u1 squared. Right, and then this would now be, again, x3 times u2 squared, right, etc. You basically just have to keep adding this to all of these. And all that does now is it's going to add on to your A matrix. So I guess in this case, with our weird kind of format, I guess going to kind of move this over a little bit, right? And now this becomes u1 squared, u2 squared, u3 squared, blah, 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 u3, or, sorry, uns. Squared, right? And again, I probably should have rearranged the columns, but you get the idea, right? So even though you have a non-linear or a polynomial function, if you can extract the coefficients in sort of this linear fashion, you can basically boil this down to an AX is equal to B. It just now depends on what is your A matrix going to look like, right? So with that being said, now let's jump over and talk about actually solving AX is equal to B for this over-constrained problem. All right, so we've got this ax is equal to b for this over-constrained system, so we're not going to be able to solve this exactly. So instead, maybe the next best thing we can do is, can we solve this by choosing an x which makes the left-hand side equal to the right-hand side as much as possible? In other words, we would like the difference between the left-hand side and the right-hand side to be as small as possible. So the trick here now is to quantify what do we mean by error and as small as possible, all that sort of stuff. So what we mean by that is, in this particular case, one thing we could do is we could look at the difference between, again, the left-hand side and the right-hand side. We could then take the 2 norm of that, we could square it, and then sometimes what you'll also see is sometimes people will throw in a 1/2 in front. We'll see later on down the road why that matters and why that's a little bit helpful. For those of you who are familiar with optimization, though, you know that just scaling your cost function, your objective function, by an arbitrary scalar is not going to actually change your optimal solution. So we don't have to worry about this half too much. Instead, let's focus on some of these other terms and what does this mean. So again, the first thing maybe we should call to your attention here is this function e. This is sometimes referred to as your error function, or in more general optimization terms, this is sometimes referred to as your cost function. In statistical circles, this might be also referred to as your loss function. They all mean the same thing. All this thing is, it's a function which is going to be able to look at a solution x here and basically tell you with one scalar number a value of cost or error or loss or something that you can try to optimize against, right? So this is our cost function or our error function. It's this particular thing where, again, what it looks at is the difference between ax and b, takes the 2 norm of it, squares that, and then takes a 1/2 in front, okay? So let's look at this and see, what does this thing actually look like? So I've written it out a little bit for our particular case. So again, you can see that the ax, in fact, this is what we just erased. We had this on the board about 30 seconds ago, right? This here was our linear function for all of the different data points in our sample, right? So the first row was just, here's the linear data point for basically the, the linear function for the first data point. So again, this thing right here, you can think about this, this is just y1, right? It's the function's output for the first data point. And then this b, right, was just d1, okay? And then same thing, this other point right here, this is just y2 minus d all the way down to y and s minus d. So again, you look at this, the difference between the model's prediction and the actual output, that's the residual, right? So this whole thing, in fact, if I want to use another color, let's call this in purple. This entire term right here is just R1, right? It's just the first residual. Same thing with this one, right? This is just R2, and this entire thing down here is R3. So now all we're talking about is this vector is just basically R1, R2, R3. I now need to take the 2 norm of it, right, which is I'm still drawing these vertical bars. How do you take the 2 norm of a vector? Well, you just take this component squared plus this component squared plus that component squared, square root the whole thing, right? So that's what I've got down here, right? It's the first component squared plus the second component squared plus yada, yada, yada. The last component squared, square root the entire thing, right? And now you can kind of see why there's a square outside here, is this square outside will cancel the square root on the inside, so these things go away, and you just end up with this, right? And again, if you stare at this thing long enough, the easier way that I could write this is just, it's a sum, right? This error function is just basically 1/2 times the sum of all the residuals squared, right? So this actually, because of that fact, right, but you can see by the construction, this is sometimes referred to as the sum of squares or squared residuals. So this particular cost function has this particular name because of how we've constructed it, right? All this thing does is it takes all the residuals, squares them, and adds them up, right? So that's the overall cost function for the problem or for our optimization system. One thing that we might want to make a note of here is this e, right? This error function. Look at it. It is a function of a lot of different things, right? Things that go into it is obviously the tunable parameters x, right? You see x1 and x2 show up all over the place, right? So this error function, by changing those tunable parameters, x1 and x2, you change the value of this cost function, right? Another thing that shows up everywhere is the actual data, right? U1 and D1, U2 and D2, UNS and DNS, right? The real data shows up in here. So this error function also will change depending on what your data points are, right? Or what data you're feeding it, right? Okay, so maybe also down the road, it might be useful to look at, you look at this formulation, you can see it's basically all you're doing is you're taking the residual or the error contributed by data point number 1, you're adding that to the error contributed by data point 2, et cetera, et cetera. So we might want to break out the error contributed or created by one individual data point. Let's call this E sub c, okay? So E sub c is, again, just 1/2 times the residual for that particular component or for that particular data point squared, okay? So you might see this referred to as like the sub-cost function or the minor cost function or the individual error function. All we're talking about is the contribution of one data point to the overall error function. Okay, and again, we're going to revisit this later. So I just want to put this on your radar right now because this will come up in later discussions. Okay, so now at this point, I think we have a pretty well posed problem because I have a cost function here. We know what we're trying to optimize, namely we're trying to pick these tunable parameters x, and really all we're trying to do now is choose these x's so that that cost function is as small as possible. So from an optimization perspective, we can pose this as a problem that looks like this, right? I am basically looking for the x value, and again, it can be any member of R2, right? It's just two elements. I just need an x1 and an x2. That's all I care about. I want to pick those two magic numbers such that it minimizes this error function. I'm going to call that my optimal solution, right? So again, at this point, we can basically throw away all this discussion about data science or throw away, this idea of regression. We've boiled this down to a optimization problem, right? And we can now just talk about this from a sterile mathematical optimization perspective, okay? For this particular case, right, because this error function is this sum of squares residual, and because it's this simple problem, right, of a linear regression of basically solving ax equal to b, people much smarter than me have studied ax is equal to b for a long time and have come up with a lot of really good analytical solutions. So this particular cost function here, this sum of squares residual, this problem, if you are using that particular cost function, this has a closed form analytical solution, and that's given by the Moore-Penrose pseudo-inverse. So these were two mathematicians who independently actually developed this solution to this exact problem of solve ax equal to b by minimizing this sum of squared residuals. Okay, so the Moore-Penrose pseudo-inverse is given by this. So sometimes it's written as a, like a dagger. All right, so this A dagger is basically you take your A matrix, transpose it, times it by itself. You take the inverse of this thing and then multiply by A transpose again. What this is, it's sometimes referred to as a pseudo-inverse because you know that in this case, there's no such thing as the inverse of A, right? Because it's not even square, right? This thing is long and skinny, so you can't, there's no such thing as an inverse, but there's a pseudo-inverse or a quasi-inverse, which is this thing right here. So if you now just go ahead and left multiply both sides by the pseudo-inverse, you get an x which minimizes this error function in this situation, right? So in this case, you can just plug it in. For the data set I showed you earlier, in fact, we'll jump over to MATLAB and I'll show you how I implemented this in MATLAB. MATLAB has a command called PINV for pseudo-inverse, which basically implements this, this calculation here. And what it does is, for that data set, we end up with some solutions, and you can see this is what that fit looks like. And you can see that fitted model looks quite nice. It goes right through the center mass of that data, and it looks, yeah, pretty darn great. So I don't want to spend too much time on this. Like I said, we will jump over to MATLAB, and I'll show you the code I used to generate this in just a second. But before we do that, I do want to talk a little bit about, let's back up and think about how we got here, right? We got to this point of formulating this as an optimization problem. And now what we did in this particular case, because we had this nice linear ax equal to b with a sum of squared residual cost function, basically we had a very specific optimization problem, and then we knew we could stand on the shoulders of giants, namely Moore's and Penrose, and use their pseudo-inverse to solve this. We could analytically solve this right here, right now, right off the bat, right? What if we weren't that smart, right? Or what if we didn't know how to solve this analytically? Could we instead employ a numerical scheme to try to solve this optimization problem? So again, we've got plenty of other videos on the channel talking about numerical optimization routines, and that's exactly what they do, right? You take a hard, complicated optimization problem, one that you might not be able to tackle analytically, and instead let's throw numerical techniques at it. So again, I'll refer you to a couple of these other videos if you want more information on that, but let's just assume you're familiar with that and leverage one of these algorithms, namely numerical gradient descent. And let's see if we can actually solve this problem here from a numerical perspective and see if we get a similar answer to the analytical solution for this regression problem. All right, so we've got the numerical optimization problem posed, and now we have to ask ourselves, how can we implement a routine that would help us solve, or basically find the minimum of that cost function that we just discussed? In fact, for this particular case, we can actually immediately visualize the cost function. I'll show a screenshot of it right here, and as you can see, this is just a cost function with two parameters, right? It's an x1 and an x2, or a slope and an offset, right? Those are the two things that we're optimizing over. Those are the two numbers we're trying to pick. So really, I can just think about plotting this cost function over all possible different values of slope and offset, and we can ask, where is the minimum of this cost function? So hopefully by looking at this picture and hearing this discussion, hopefully alarm bells are going off in your head and you're thinking, oh yeah, something like gradient descent or something like that is going to help me be able to find one of these minima of my cost function numerically, right? So one of the key things that pretty much all of these or a lot of numerical optimization routines require, including gradient descent, in fact the name is right there in gradient descent, is we need the gradient of the cost function, right? So again, remember, the gradient of the cost function is nothing more than the partial derivatives of the cost function with respect to the optimization variables or the decision variables or the tunable parameters of your model. So in this case, since we have two tunable parameters, we basically have two sets of partials we need to take. So again, I just want to draw to your attention. Remember, we said the number of tunable parameters for our case were just two, right? Okay, so I need to calculate the gradient or the partial derivative of my cost function with respect to the first tunable parameter, and I also need to calculate the partial derivative of the cost function with respect to the second tunable parameter. So that's all the gradient is. So let's just go ahead and write this out a little bit. So remember, the cost function we said was basically the sum of all of these individual or minor cost functions that we talked about earlier, right? So the nice thing about this is I wanted to take one moment to just point this out, right, is the partial derivative operator is linear. So in the sense that instead of having to compute or add up together all of these individual cost functions and then take the partial, I can actually move this partial operator and take the partial of this little minor cost function, add it to the derivative of the second minor one, etc., etc. So that's all I've done in this step, is I've moved that derivative or that partial differentiation operator to each individual component. Again, I just wanted to call this out to your attention, right, that because this partial derivative is linear, it is allowed to be distributed into these individual components, and this is going to come into play, again, in a few lectures when we start discussing things like stochastic gradient descent, but this is what it is right now. We're not doing anything fancy. I'm just distributing it in here. Now, the other reason I wanted to bring this up is now you can see, here's what the gradient looks like. What it is, let's look at each one of these terms. I need to take the partial derivative of the first minor cost function. So this is, again, the cost or the loss function or the error function due to the first data sample, right? I need to take its derivative with respect to the first tunable parameter, right? Then I need to calculate another partial derivative right here. This is the partial derivative of the second minor cost function, right? Or the error due to the second data point or data sample in my set, right? I need to take its partial with respect to the first tunable parameter, etc., 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 right? And then the second line of this gradient is the same idea, except now instead of taking partial derivatives with respect to the first tunable parameter, I'm now taking partial derivatives with respect to the second tunable parameter, right? Now, if you stare at this thing long enough, you basically see that, okay, how many of these partials are there in this first row? Well, you can see here that there are basically ns partials in this first row, right? Because there are ns number of samples in my data set. Each one of these terms corresponds to the partial of my error function, of my minor error function with respect to a given sample with respect to the first tunable parameter, right? Same thing down here in the second row, we also have ns terms. So you think about this, we basically have ns terms here, then we have basically np rows of my gradient, right? That's the number of tunable parameters. So the thing to think about here, and again, I'm calling this out to kind of prime the pump for some of our future discussions, is think about how many partial derivatives you actually have to calculate in here. So the total number of partials, right, that you have to compute is what? It is actually, in this case, theoretically, it's ns times np, right? And again, the reason I want to call this to your attention right now is because think about this. In modern data science, right, what is ns? Ns is the number of data samples in your data set. What is this number for a lot of reasonable cases, right? This is large, right? You have a lot of data. You have thousands. You have millions. So ns is big, right? There are a lot of potential minor cost functions that you're going to have to compute. Then you're going to have to take their derivatives. Let's look at np. What is np? NP is the number of tunable parameters in your model. For this simple case, I just have a slope and an offset. But later on down the road, we're going to start looking at things like neural networks, where neural networks have millions of parameters, right? There are millions of weights and biases and things like that. So again, NP is also huge. Do you see where this might become a problem? You got a huge number multiplied by a huge number. You got an even huge, well, I don't think huge-er is a word, but you've got a problem here, right? So again, I just want to call this to your attention because this lays bare what one of the critical blockers or critical bottlenecks are in this situation is if you wanted to do this, quote unquote, properly and right, you need to compute a lot of partial derivatives, right? It's going to be no problem here for our little toy academic example, but when you start scaling this up to a real production system, you might have problems, okay? Okay, so that being said, let's go back to Candyland with our academic example and think about, okay, how do I do this? How do I calculate these partial derivatives, right? That's what I need to do, okay? So there's a couple of ways to calculate partial derivatives. The first is, probably the most obvious is just analytically calculate this, right? Just, what the functions are, just do it, right? So let's do that right now. So you can see, okay, here's the first term, right? This is basically it's the squared residual, right? So you can see right here, this term here is the residual, right? This is the residual R1. You just square it and put the 1/2, right? That's all this thing is. And same thing, you just do this for R2, blah, 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 all the way here. Here's the residual R and S, right? Square them. Again, nothing fancy. This is just the sum of squares residual that we talked about earlier. But now all I'm going to do is I'm going to take the partial derivative of this residual term with respect to x1. And you can easily see this isn't hard, right? Here's the x1. Sure, it's embedded within a square, so I can do a little bit of calculus, but this is not too hard. I'll just jump over to Mathematica, have it solve this for me, take this partial, then I'll move on to the next one. Take the partial, 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 right? Blah, 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 I'm done. Then let's move on to the second row. This is even easier here because I'm taking the partial with respect to x2. x2 is sitting here by itself. It doesn't even have a coefficient term, so this partial is even easier. So again, you can just blast through this no problem analytically. In fact, this is what you'll end up with. If you go to Mathematica, this is what you'll end up with. So here it is. So again, not too difficult. And again, you can see what ends up happening is here's this residual term R1. Here's R and S. Again, you see R1 show up, and you see R and S. So all of this turns out to be the gradient for this particular case, for this particular cost function, is actually pretty darn simple, right? It's just this and this. So here it is. I analytically computed it. We can go run over now and implement this. I can make a function where you tell me all these parameters, and I can now figure out what is the gradient. So I've got the gradient in the bag right now. The catch being, right, again, think about it. We had to analytically calculate ns times np gradients, which if this function was a little bit more complicated, this maybe might not be so trivial, right? Okay. That's one way to calculate the gradient. what are some other techniques? Again, I want to just throw this out here now to help prime the pump for some future discussions. Another way you could calculate the gradient, right? Or gradients are just partial derivatives, right? You can calculate partial derivatives numerically, right? In fact, we have a dedicated video talking about how to calculate partial derivatives, basically using perturbations, and basically you're just doing rise over run, right? It's nothing fancy. That's all you're doing. You're numerically perturbing the gradient a little bit, and you're just doing a finite difference scheme to basically compute the gradients numerically. So this is another option, but again, we're going to come back to this later when we start talking about things like backpropagation. Why might this throw up some klaxons and some warning sirens should probably be going off in your head right now when you think about numerically calculating a huge number of gradients, right? Okay? And then the third method is you could think about calculating these partials using the chain rule. And I'm going to leave this like this now. I'm not going to explain this more because we are going to have a complete discussion. This is the discussion on backpropagation for some of these systems where we're going to calculate these in an efficient way. So hopefully this will help ameliorate some of the problems associated with this explosion of dimensionality problem. Okay. So anyway, that's it, right? So what we're trying to do, again, there's a lot of stuff we talked about here. The key takeaway for this section is all we're trying to do is get the gradient, right? A lot of these numerical routines depend on finding the gradient, and in this case, that's exactly what we did, right? I've got the gradient in hand right now, so now we can think about going and implementing some type of numerical optimization routine to use this information and find us an optimal solution. All right, so with all that infrastructure in place, the next step is actually really easy, right? So now that we've got the cost function, we've got the gradient of the cost function, now we're ready to just implement pretty much a numerical gradient descent algorithm to numerically solve this problem, right? So the idea is we're going to start at some random guess at the optimal parameters for my model, right? So pick a random slope and a random offset, right? And the idea is we would like to improve this point to go to another point or another set of model parameters, x1, and we're going to check, is that good enough? If not, let's go to x2, and we're going to keep going like this until we reach some termination criteria and we obtain an optimal solution for the model parameters that minimize the cost function that we have previously discussed, right? So that's all we're doing, right? Is we're basically implementing a numerical optimization routine. There's plenty of different choices. The thing that we want to use is gradient descent. And again, we've talked about this in other videos, so I'm going to assume you're familiar with those concepts, and let's just talk about it right now and see how we can implement it in this case. So again, you remember we said the way we're going to choose our next point, x of k plus 1, is we're going to look at the current point or the current set of model parameters, and then we're going to basically take a step in the direction dk by an amount alpha k. So remember, this was basically your descent direction, and your step size was given by alpha k, right? So this is what we had, okay? So for gradient descent, all we're going to use is our direction of our step. It's just going to be in the negative gradient direction, right? And again, this is why we did all this work to get the gradient calculation, is because we can use it right here in our gradient descent algorithm, okay? The only thing I do want to maybe mention is please don't confuse this d sub k. It's not the same thing as d, which we used earlier to denote the desired output or the label or the actual output of the system, right? So just don't confuse this. In this context right now, when we're talking about the numerical optimization routine, d sub k is the descent direction at step number k of your routine, right? And again, for this case, our step size is, let's just do something really simple. Let's just choose a constant step size. There's, again, plenty of other discussions we've had on the channel talking about how to choose the step size. You can do things like the Armijo rule. You can do things like line minimization. But for this case, let's just choose a constant step size to keep things easy. So with that being said, this is the idea. I think what we should do is let's jump over to MATLAB and just implement this routine, write a little bit of code, and I'll show you the results of what does this look like when we actually implement it for this particular situation where we're trying to fit basically a line to the data. All right, so let's go ahead and give this a try in MATLAB. So let me draw your attention over here to the left. So I've just created a real quick script that loads in some of this data, which I showed earlier, which is just those pairs of U's and D's. And let's just run to this breakpoint, and I'll just show you what the data looks like. And again, this is the same picture we showed earlier, and we said, yeah, this sure looks like a linear kind of relationship. Let's go ahead and try to fit this with a line. And we're going to first do this using the Moore-Penrose kind of pseudo-inverse approach, right? So in order to do that, we went ahead and made our A matrix right here, which you can see is just all of the U's followed by a big column of just ones, right? The B vector is just this D vector that we've got. And with that in place, we can basically go ahead and compute the Moore-Penrose pseudo-inverse like we saw on the board. And what I do want to do in line 37 here is I just wanted to show you that this A dagger that we compute via the Moore-Penrose pseudo-inverse kind of formula, as you see here, is the same thing as MATLAB's P inverse, right? So if you just say help P inverse, you'll basically see that this is basically the Moore-Penrose pseudo-inverse. And I'm just checking here that, yeah, P inverse gives you pretty much the exact same thing as here, up to 10 to the minus 15th in every element. So I just check that. Assuming that passes, we're then going to go ahead and just use that pseudo-inverse to compute the optimal least squares solution of this problem and get our optimal values of our model X star here. And I'll just print them to the screen. So let's just go ahead and I'll run this just to show you what we end up with. And yeah, these are the numbers we showed earlier. And again, this is basically telling us that we anticipate this line to fit here has a slope of negative 2.302 and a y offset or a y-intercept of 5.6986. So let's just go ahead and verify that that actually works. So I've gone ahead and created a little function f, which you can see is nothing more than, if you look at this here, it's basically just saying, you tell me the model parameters x, and you give me some data, and I'm just going to fit the model, which in this case is the linear line, or the affine fit right here of just slope times the inputs plus the offset, right? So that's all that does. So that computes our y values, right? This is the model predictions, and that gives us enough now to also produce the residuals, just if we're interested, right? So we can see the difference between the actual output or label and then what the model predicted here. So let's just go ahead and plot that so we can see what this looks like. So I'll just run the rest of this code. And let me pull it up here, and there you go. And as you can see, this works quite well, right? If you expand this, let me blow this up a little bit. So again, you can see that the red are obviously the actual data or the training data or the label data, however you want to call it, right? And then these blue circles are the model's prediction at all of these independent variable input U's, right? And then I'm trying to draw the residuals as these sort of magenta vertical lines. And as you can see, what we're doing is we're basically trying to fit a line to this such that the sum of the squares of all of these residuals is minimal, right? So as you can see, this approach worked great. And by looking at the script here, you see there's no numerical iteration. There's nothing like that, right? It's basically a direct solve right here. But we could do that because we had this linear regression problem, right? Now, if we didn't have that, that's when we would have to jump over to the numerical solution. So let's go ahead and take a look at that for this particular linear line fitting problem. All right, so this is the approach that we talked about on the board of just setting up the problem as a numerical optimization problem and using gradient descent to solve it. So again, I've just got another script which tries to solve this same problem in a different fashion. So to do this, let's go ahead and run this again, and I'll just show you I'm loading in the exact same data, right? So the inputs or the constants or the givens of this problem are the exact same, right? We just have some labeled training data, or we have a data set that we want to fit it with, right? So what we can now do with this particular problem, right, is we saw that, okay, we know what the cost function looks like, or the loss function, so we can go ahead and plot that for all possible values of the slope and the offset. So let me go ahead and run this next section, and I'll just show you what that kind of looks like. And again, this is, we did look at this, I think, on the board earlier, right? So the only thing nice about this is now we can sort of spin this around now, and we can see that this is what the loss or the cost function looks like for any given values of x1, right, which was the slope, and x2, which was the offset, right, the y-intercept. So as you can see, what we're really looking for is we are looking for the combination of x1 and x2 that are, it's kind of down at the bottom of this bowl, right? That's the whole idea with gradient descent, is we start at some probably large value of e, or my cost function, and I want to descend down this gradient or walk down this surface until I reach some local minima, right? So that's all we're going to do in this next set is I'm going to pick a guess. Let's just go ahead and start with a guess of model parameters of just 0, 0, right? And now we're going to use just a constant step size of alpha of 0.02, and let's just take 15 steps here. And all we're doing is, in this block of code here, is I am just setting up that gradient descent, that numerical descent optimization algorithm that we talked about earlier, where you can see is all I'm going to do is I'm going to obtain the cost function at the current location of xk. And for giggles, we can open up this function if you want to see what it looks like. And again, this is basically just the sum of squares residuals. You can see it right here, right? Here's the 1/2 residual squared, and then you're just going to add that up for every single individual cost function. I'm going to do this for every single input or every single data set or data sample I have in my set, right? So that's all I'm doing is I'm evaluating the cost function at a particular choice of model parameter. So the first time through this, we are going to get the cost associated with trying to fit the data with a line of slope 0 and a y offset of 0, right? And that's probably going to be horrible, so this cost is going to be high. But what I want to then do is we are then going to compute the gradient of the cost function. And again, we showed how to do that on the board. So this here is nothing more than that implementation. As you can see, if you stare at this long enough, this is basically just a numerical implementation of the gradient that we worked out analytically on the board. So I'm just going to write a little function to compute this for me. And that's going to give me the gradient of the entire cost function. So the thing to maybe call to your attention right here is this is the full gradient, right? It's the gradient using all of the data points and all of the samples, right? So this is the gradient. So the descent direction I'm going to use for my numerical optimization algorithm is just the negative of the gradient, and then I just iterate, right? So that's all I'm going to do, and I just do a little bit of plotting down here. I'm just going to plot where we are on the cost function. In fact, let me just pull this back up. Sorry. Right. I just want to see where we are as we progress. And you know what? Let's just go ahead and let this thing rip, and I'll show you the results actually in just a second. Oh, you can actually kind of see it doing here. It's updating. So we started up here, right, of x1 and x2 of 0, 0, and you can see that had some pretty poor cost. And in fact, let me pull up this other plot where I do plot the cost versus iteration number. So you can see initially we've got some, the cost, the sum of squares residuals is like up there at, I don't know, 550 or something like that. But what we can do is we can go ahead and walk down in the direction of the gradient, or excuse me, in the negative gradient, and take a step size of this constant value of 0.02 times the dimension of the gradient, or the norm of the gradient, right? That gives us our actual step size. And we basically step from here down to here, right? So that's our first step. And in fact, maybe what we can do is if we look at this in sort of a top-down fashion, maybe that's the easier way to look at this. Let me blow this up, right? So here's our first step, is we go in this direction, and that brings us to here when we take that step size. And then we just do it again, right? We descend down the hill as quickly as possible, and again, and again, and again, and again, and again, until eventually, yeah, it looks like this gets us down into some local minima, right? And what that does is, if we go ahead and look at the results, it looks like, I think I printed this out. Is this what I'm doing down here? Yep, here, I'm displaying the results here, right? This is the optimal solution of our model parameters obtained via numerical optimization. And as you can see, this is pretty much the same value that we got earlier. And I'll show you one more graph that I made during this process. And this is sort of the state of how the model progresses as we iterate through the this process, right? So what you can see here is the dark blue line is the model prediction at the first set of model parameters in this process, namely at if you 0, 0 as your model, right? You can clearly see this is a model that says the slope is 0, the offset is 0, and you get a horrible fit, right? This line does not go through any of these red data points, right? But when you take one step, then suddenly we come up to here, we get a slightly better model. You can see this line is fitting the data a little bit better. And again, you just iterate and iterate and iterate and iterate and iterate until we finally get this dark red line, which is basically the same line that we got via the Morse-Penrose kind of analytical approach, right? So as you can see, this process is incredibly powerful because it allows us to start with some arbitrarily high amount of error, but this numerical optimization routine is going to allow us to step down, and we're going to keep burning down the error every single time until we get, to some acceptable level of tolerance, right? And as you can see, the gradient, right, is also going down. The norm of the gradient is getting down. So we are getting to a local minima. We're starting to converge. So this numerical approach is great because, again, it got us pretty much the same result as that Moore-Penrose approach, except it does this in a much more sort of agnostic model agnostic fashion, right? It didn't require any particular structure. We could just throw the numerical optimizer at it and it gets us a model that is fitted to the data, right? And just for completeness, since we've got MATLAB up, why don't we also go through that quadratic example just to show you that this exact same approach that we walked through on the left will work over here on the right. And on the right, the only difference now is, let me go ahead and change the folder. I'm going to execute this script here on the right. This is virtually identical to the previous, except now let's look at this data set, right? So you can see this data set does not look linear. It looks quadratic, right? But as we showed on the board, you can basically still formulate this as a linear regression problem. As you can see, the A matrix, in fact, maybe it might be good to just put both of these two next to one another. You can see that the A matrix is just different by one column, right? So all we add on is this extra column of U squared. This is now going to increase the dimensionality of our model, right? So now we have 3 model parameters, not just 2. But again, the rest of the code is absolutely identical, right? You can still compute the Morse-Penrose inverse. Sure, the dimensions are different, but at the end of the day, we now get an optimal solution here for a quadratic model fit. So again, this model is now, here's the slope, here's the constant term, and here's the coefficient of the squared term. So again, for giggles, what we can do is look at how that fit. And look at that. Here's what it does, right? Again, the Morse-Penrose sort of one-shot analytical approach gets you a very nicely fitted quadratic, which does seem to go through the majority of these points and nail it as best as it can. And again, we can do the same thing. We could say, all right, forget this Morse-Penrose approach, just throw it at the numerical scheme. And again, you can see the numerical scheme is pretty much identical, right? It's I might have to tune some of these parameters a little bit different, right? So maybe I need a different step size and maybe I need a different number of steps. You can play with these, and by playing with your step size, you can get different behavior. You can maybe converge to different minima, but in this case, we don't have to worry. It works out pretty well for this. So let's go ahead and I'll just do this again. And again, if we just compare, you can see that these two sets of code are almost identical. The only difference is the cost function gradient is a little bit different in both of these cases. So for completeness, let me pull up, whoops, oh shucks, sorry, I'm in the wrong folder. Sorry, this is the one. Here's the cost function gradient for the line. Here's the cost function gradient for the quadratic. And as you can see, the only difference is now we have a third term in the gradient because we need to take the gradient of the cost function with respect to now 3 model parameters. But again, the overall setup is the exact same thing. So if we run this over here on the right, it's exactly like we did earlier. And in fact, give me a second and I'll pull this up for you. So again, you can see here is how the error or the cost function value decreases over time. And now you can see as well, here's how the model fit evolves over time. So as you can see, initially we start with 0, 0, 0. Again, a flat quadratic, right? Which does not do well in terms of hitting the red X's. But as we iterate through, this thing starts bending, 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 and we are basically starting to fit the data iteratively using this scheme, right? So again, this is incredibly powerful because if you step back and think what happened, right, is we started from an arbitrary guess of a model, right? This model is, maybe you can call this untrained, right? This model is not trained on the data. It's not set or to fit, or it's not tuned to fit the data, right? But what we do is we start from that random guess and we iteratively now, via numerical optimization techniques, fit the model parameters to the actual data so that it matches as best as it can, right? And again, I did briefly mention that some of this is black magic in terms of how you pick these parameters. So for example, if you change this parameter, like let's bump up the step size a little bit by a factor of 3, and I don't think this, let me see if this is going to cause a problem. Yep. Okay, hold on. Let me show you what ended up happening here. So now, look at this. The error, it's starting to increase. We've basically made the system unstable, right? It's oscillatory, or it's just completely exponentially unstable. This step size is too big, so you can see what we end up with is models that just diverge from the local minima, right? So we don't actually converge. So you may have to play with these numbers a little bit to get convergence to the behavior that you like. But if you play with this is a lot easier than trying to randomly guess, right, how to fit these model parameters. And again, this might work well for, or it might be easy to analytically compute 3 model parameters. But again, think about it. Instead of a quadratic, what if I wanted a 4th order, a 5th order, a 10th order polynomial to fit this, right? The number of model parameters could go up. This scheme doesn't care, right? Sure, you might have to compute a slightly more complex gradient, but this overall structure is going to work, right? So let's see how this might be helpful if we had maybe a more generalized regression case, something that maybe isn't going to fit in this linear formulation of this analytical least squares via the Morse-Penrose inverse. So let's hop over the board and take a look at a more complicated model that we would like to fit.
All right, so we saw that worked quite well for linear regression. And again, the reason linear regression was so convenient, right, is because it allowed us to kind of directly obtain a solution via this analytical least squares. Now, let's think about how about if we wanted to remove this restriction on linear regression, and maybe let's now talk about just generalized regression. Okay, and the difference now is that we now suddenly cannot formulate this into a big ax equals to b, so this option is no longer viable, right? So we can't use analytical least squares. We can't use the pseudo-inverse to go ahead and directly solve our ax is equal to b to get our model parameters to fit the data, but this is still totally available to us, right? The numerical optimization routine via gradient descent it's not going to blink an eye. It doesn't care what the model is. Maybe with a couple of asterisks, there's a couple of caveats. We're going to see there's a couple of minor tweaks that we might have to make, some complications, but this is still viable, okay? So to illustrate that, let's think about maybe another set of data. So again, over here's a screenshot of some other data, and as you can see, I don't know, this looks a little bit more odd, and maybe we don't want to try to fit it with a polynomial or something that would fit into linear least squares. What if we wanted to try to fit this data over here to some more complicated model, right? So the complicated model that I'd like to look at is it's actually not that complicated, but it's this composite function where, again, you have u coming in, the model predicts an output y, but the way it's going to do this is it's going to do 2 operations. The first I'm going to call row. So row is just taking the input u, and again, it just uses a line, all right? You can see this w is basically the slope, this b is the y offset, y-intercept, just like we saw earlier, and it does this linear or affine operation to compute a signal z, okay? This signal z then is then run through another function, which is called sigma, which takes this form, this 1 over 1 plus e to the minus z. And that is how it computes y, the output, okay? So again, you can see that this function f, it's sort of broken up into 2 composite functions, right? First, it takes the input u, runs it through row, then it takes the signal z, this intermediate signal z, runs it through sigma to get y, okay? Now, this might look a little weird, but again, the reason I wanted to use this particular function is this is actually pretty much the simplest form of a neural network that you can come up with. In fact, the sort of equivalent neural network diagram that you might see is something like this down on the bottom. So this is what you might see people draw for a neural network, but this is really what it's doing behind the scenes, right? All we're talking about here is a single layer neural network where you have basically a single input layer here. You have a single output layer, so there's no hidden layers, but basically you'll see this kind of diagram where now there's weights associated with going into this output layer. There's a bias associated with this output layer, and that's how it computes the output. And again, the way it takes these weights and biases into account is just via these two functions that we've got up here, okay? So again, this is another part where I just wanted to prime the pump and kind of get you ready. Let's talk about using a regression framework to basically try to fit this super duper simple neural network to the data we saw previously using the techniques that we just discussed, this numerical optimization and gradient descent. So again, this is a really simple case. We're going to look at much more complicated cases in the future, but this is the foundation and the groundwork for it, okay? So the idea now with this is, again, yeah, you can think about this as a neural network, or you can think about it as it's just some function, right? It's a function with tunable parameters, right? So the first thing we should maybe think about is let's just get a rough idea or a feel for these rho and sigma functions. So obviously rho is really simple, right? It's a line, right? So you can see that I just made a plot of some rho versus u values, and again, you get different lines depending on the weights and the biases, or the w and the b's, or the parameter 1 and parameter 2, however you want to think about it. You can see that these are two of the tunable parameters of the model, right? You basically mess with the weight and the bias. It's basically messing with the slope and the offset of these lines, right? So these are two tunable parameters that we get to pick in our model, right? Now, you look at this sigma function and you see actually there's no tunable parameters of your sigma function. This sigma function, if you plot it, it just looks like this sigmoidal shape, right? This is actually, you know, again, for for priming the pump, right? This is sometimes referred to as like an activation function or an activation layer, right, in your neural network. But it has this general shape. So again, if you look at this, right, and you boil it down, you see that all this thing is, right, it's a composite function that looks like this, right? So here's how the function works. You basically give me the input to the function u, you give me the two tunable parameters values that you want, namely the weight and the bias, and this will spit out the output of the system y, or the output of the function y, by running it through this composite function. You can kind of see here is the sigma portion, and then the overall is the, here is the rho portion, and then the overall part is the sigma portion, or the overall function mapping, right? And we can see that this is a function where we have, again, there's only two tunable parameters to this, right? So at this point, all we need to do is basically start thinking about, okay, how do we go ahead and get this into our numerical optimization routine, right? So let me just go ahead and I just want to scroll here to the right portion of the notes here. Okay, so it's the exact same thing we did earlier, right? There's no difference. The only difference is the function that we're fitting is a little bit more complicated, and as you can see right here, there's no easy way to extract x1 and x2 out in sort of vector form, so we can't turn this into an ax is equal to b problem like we did earlier. So in other words, it's not a linear regression problem, but that doesn't stop us from going ahead and still computing a cost, error, loss function, whatever you want to call it, for this particular model, right? So again, let's use the exact same thing we did earlier. Let's just use our sum of squared residuals as our loss function, right? So again, this is the exact same formulation. This we saw earlier. The residuals are just the output of the model minus the actual label, right? Or the actual output of the real system, right? So that's the exact same thing we saw before. Now, the only part where this gets different now is how is this y computed, right? How does the model compute the its prediction of the output, right? Well, that's what this function, this more complicated function is. So just go ahead and stick that in for each one of these terms. And again, this looks very similar. It's just going to be, here's the individual or the sub-cost function for data point number 1, right? You can kind of clearly see here that data point number 1 shows up here. Here's U1 and D1 shows up. So this is the cost associated with term 1, right, or data point 1, or I think we can use the notation E1, right? And then there's also a term, right, E2, E3, all the way up to this one here, which is ENS, right? Because you see, obviously, sample number UNS and matching DNS here. So again, the cost function, right, is just a summation of all of the individual cost functions associated with each individual data point. So again, we saw this before. It just looks a little bit different. It's a little bit more complicated because the function's a little bit more complicated. But at the end of the day, we still have an analytical description of this error function, right? Therefore, we can take the next step of basically calculating this gradient with respect to the two tunable parameters, right? So again, gradient, this is the exact same thing we saw earlier, right? The definition of the gradient is unchanged, right? It's just the partial derivative of the cost function with respect to the first tunable parameter, cost function of the partial of the cost function with respect to the second tunable parameter. And all we got to do now is just calculate the derivative of this thing with respect to E1 and then with respect to E2. So again, you can see it's a little bit more complicated, but we can still do it analytically. And in fact, I'm not going to waste the board space to write it all down. In fact, I'll just show you a screenshot of me doing this in Mathematica so you can see, yeah, it's not complicated. You just need to take partial derivatives. But again, we run into that same issue of dimensionality in the sense that if you have a lot of data points or samples, that gradient calculation involves a lot of analytical gradients. So again, we were going to have to address that down the road in one of our future discussions. But for now, for this toy problem where you have maybe 20 or 50 data points, it's not a problem, right? We can do this in Mathematica and just bust it out, right? So with that, I think we've got everything in place. Maybe the one thing that we should talk about now is you saw that really this idea of, a neural network is very much an AI ML kind of concept, right? You hear a lot about this in artificial intelligence and machine learning circles, but we now see that really the neural network, it's just some function that we are going to fit or train using generalized regression. So again, maybe what might be helpful is let's talk a little bit about, you might see a lot of AI or ML terminology versus now we saw really this is just optimization, right? So when you see things like, people talk about in AI of training data, right? You need a whole bunch of training data. Oops, I spelled that wrong. Training data, right? Everyone talks about you need training data in order to train your network. Well, what are they really talking about, right? It's just a data set, right? It's just a points of inputs and outputs, right? Or inputs and labels, right? So this is really, from an optimization perspective or a regression perspective, this is just a data set, right? That's what training data is. And then the next thing you always hear about in AI is, right, or with the neural network, is you want to train your network or train your classifier, right? You're training your system. So a lot of people seem to make it sound like this is some magical black magic training process where you have to do something, like we don't really know what it is, but a lot of people will say, oh yeah, I trained my network, I trained my classifier using the training data. Well, what they're talking about here, right, is we clearly see that from an optimization standpoint, this is just performing basically numerical gradient descent or performing a numerical optimization routine. So really, this is just performing numerical gradient descent, right? And then again, what else? There's things like in AI and ML, you hear about this idea of a learning rate, right? And again, this might mystify people and it might seem, complicated. Oh yeah, what does learning rate mean? It seems somewhat nebulous. It must mean something very fancy. But really now we see that from an optimization standpoint, the learning rate, it's just basically your step size, right? So again, we see that a lot of this stuff that you might see in AI/ML, again, it's all just it boils down to optimization. So a lot of these terminologies and concepts that you might see in machine learning really have parallels in optimization. So again, I like to think of it just from an optimization standpoint because I think it demystifies the process a little bit. Okay, so that's enough of the philosophical discussion. Let's jump over to MATLAB now and just implement this because again, we already built up the framework to do numerical gradient descent. So all we have to do is basically swap out the model and the whole framework we did earlier should still work. So let's jump over to MATLAB and do that now.
All right, so let's come back here to MATLAB, and again, over here on the left, this is the set of code that we were using for the linear regression. Again, this was our first example where we were just fitting a line, and now over here on the right side, let's look at how we can do the equivalent with this more complicated model. So the first thing to note is the least squares approach, right, that we did over here with fitting the line in the linear regression. We can't do that over here because we can't fit it into ax is equal to b. So let's go ahead and skip this step. But what we can do is we can still define the function f, right, which was our functional model. So again, over here was our linear model that we looked at earlier, and now this model is just more complicated, as we just discussed. It involves computing z and then computing the activation function of that z input, right? So this function is, as you can see, it's just different, but it still just has two tunable parameters, just like we saw in the linear case, okay? So now our gradient descent approach is basically the exact same thing that we did earlier over here on the left. The mechanisms are pretty much the exact same. So again, let's run this code over here on the right for our more complicated function. I'll put a breakpoint in here just so we can see what's going on. And again, let me just pull up a couple figures just to remind you where we are. So here is the data, right? And in this case, again, we can think about this as training data or our data set, whatever you want to think about it like. Here are the inputs, and then the labels associated with those inputs are basically the y values, right? So here's our training data that we want to fit our model to, and now we can basically go ahead and plot the cost function, right? So the cost function for this, it's the same thing that we did earlier. It's just the sum of squares residuals right here. It's just now that the model prediction output, right, this y sub c, is now that more complicated prediction. But at the end of the day, it still basically involves jamming all of this data in to our cost function at various different values of x, right, of our weight and bias, and that's going to allow us to basically plot the entire cost function, which looks something like this. Again, this is what the sum of squares cost, loss, error function, whatever you want to call it, looks like for all possible values of weight and all possible values of bias, again, in this small region that we're looking at. And as you can kind of see, the cost function is more complicated, right? That maybe it's not convex, it's more complicated, but I definitely can see some minima here, right? There's a local minima, it looks like, down here. So again, numerical gradient descent isn't going to care how complicated this function is. All it's going to do is basically start at some starting point, and then we're just going to descend down the gradient into one of these valleys for a local minima. So that's what we're doing over here. So let's just let it rip. Again, this is the exact same thing we did earlier. We're just going to start with some guess, choose a step size, or I guess we want to use AI ML terminology, right? Choose a learning rate right here. We're just going to use 1. And let's just take 20 steps and see where this gets us. So I'm just going to run this, and we'll continue. And you can see as we start stepping down, 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 down. Ooh, look at this. We're getting pretty close. I guess we're not getting like super duper close. It didn't look like we actually got all the way to the minima. And what we'll see is that's reflected here is if we look at how the error progresses, we can see it's coming down, but I bet if we zoom in here, this is not really getting close to 0. In fact, if we zoom in down here, we probably can see, yeah, it's not 0. We probably could keep stepping, and that might help us. What's interesting to look at here is the fits, though, of these successive models. And as we see, you start off with one it's completely wrong, right? The dark blue, it's pointed in the opposite direction. The sigmoid is kind of going the wrong way. But as we get better and better and better, look at this. We're starting to get pretty close. This red line is looking like a nice sigmoid, right? That goes through all of these data points or fits the labeled training data. So, you know what? Why don't we go ahead and restart this? So you notice here that we ended up at this location of this is the weight and this is the bias after 20 steps. Tell you what, let's just go ahead and reinitialize down here. And I'm going to reinitialize the optimization algorithm at that location. And let's tell you what, let's increase the learning rate here. Now, instead of from 1, let's go to a step size of 2 and let this guy run for another 200 iterations. So tell you what, let me go ahead and hit run on this, and maybe what we can do is that's going to take a little bit of time to run just because I've got a lot of graphics going. So give this a second and we'll be back after this finishes. All right, so that finished. So let's take a look at the results. So as you can see, here we go. Now this is looking better, right? After 200 more steps, you can kind of see the error has started to converge to kind of a constant value. And in fact, if we look at our cost function progression, in fact, let's go ahead and rotate this so we can stare at this from a top-down sort of viewpoint. I guess it's a little hard with the graphics, but you can see, yeah, it's starting to get down to this local minima. That's looking good. And then the overall function fits look like this. And as you can see, yeah, we end up with this after 200, well, I guess now it's a total of 220 total steps. We end up with this red line, which, look at that. The model is now nailing the actual data. Or if we want to talk about this from an AI ML terminology speak, right, we have trained this neural network to fit the training data, right? So that looks pretty darn nice. And I think this is probably a good spot to maybe leave it and maybe talk about concluding with a couple of ideas, right? We saw that this is really the foundation of training a lot of these AI ML models. It's basically boiling down to numerical optimization, right? That's actually what we're doing. And one thing that I want to kind of set the stage with is the reason why this is doable in these little toy problems is because we were able to implement this numerical gradient descent scheme fairly easily. Some of the things that we might need to think about here are obviously when we're thinking about calculating the cost function gradient, right? We saw that that was a potentially complicated and labor-intensive process because, as you can see here, right, we have to iterate through all of the inputs or all of the data, right? So this is where we had to basically calculate NS partials, right? There's NS partials in the dimension of the number of samples. So, right, as the number of samples U grows large, this loop is just going to get bigger and bigger, right? And then for this simple toy problem, there were only two tunable parameters. So all we had to do was calculate a D error dx1 and d error dx2. So if your model was more complicated with large numbers of these tunable parameters, you're also going to have a explosion of computational intensity and computational requirements. So this is what we want to address in some of our future discussions when we start talking about stochastic gradient descent and talking about better, more efficient ways to calculate this gradient instead of analytically doing this or doing it via numerical differencing. We might want to look at chain rule approaches such as things like backpropagation and other types of algorithms. But like I said, those are discussions for future topics. I wanted to keep the discussion here limited to the idea of using numerical optimization algorithms to perform regression. And hopefully now you've seen that, and I think you'll agree that we've covered that in pretty good detail at this point. So again, I hope you'll join us in some of our future discussions where we look at how this can now scale up to actual problems where we have much more complicated models, we have much larger data sets, and we'll do some really interesting things like recognizing characters, doing a little bit of optical character recognition, training larger neural networks, and a bunch of other applications in the future. So, like I said, with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just click on that subscribe button, it really does help me continue making these videos. And remember, the new videos come out every Monday, so I hope we'll be able to catch you at one of these future discussions, and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.